Hello and welcome to the first part of a series of videos aimed at developing a Bomberman-style game in vanilla JavaScript, using the canvas element. This classic multiplayer game was originally released by Hudson Soft for the PC Engine, or the TurboGrafx-16 console, depending on where you live, all the way back in 1990. If you're like me, you've probably spent numbers of hours in your youth going up against your friends, attempting to defeat them in its battle mode, collecting multiple power-ups to ensure you've got the edge over them, so that you can place that perfect bomb to win the game. It's that experience we'll be looking to capture in this series of videos, but obviously using the web to achieve it. By the end of this video, however, we'll be looking to build a stage background using a tilemap, and ensuring we have the correct collision in place, adding the HUD at the top of the screen that will eventually show the game state, and finally the white Bomberman himself, making him run around the map using the keyboard or gamepad. My name is Anthony, and why don't you join me in my corner of the web, where I like to build stuff in the browser with the latest technologies. Before we start, we'll first need to set up and configure our development environment and code project. To kick us off, we'll create a new repo using my JavaScript development starter template from my GitHub account as its base. If this is new to you, please use the attached video link in the upper right hand corner here, which should give you a deeper picture about what this is and why we're doing this. Ultimately though, this takes care of most of the fundamentals of creating a game in the browser, removing the need to create the initial boilerplate code, allowing us to jump right into the game we're developing. To do this, let's click the green Use This Template button and choose Create a New Repository. On the next page, decide a name for the repo and possibly a description. Then choose if you want to make this repo public or private before clicking the Create Repository from Template button. As you can expect, this will create a new repo on your own GitHub account using this template. From here you can clone this repo to your local development machine using the URL it provides. As a side note, if you prefer not to use GitHub, you can do this step manually by simply using the download zip option from the code menu and extracting the contents to a location you prefer if you feel that's more of your bag. However, for the remainder of this tutorial, we'll be running with the cloned repo option. So back on your machine, let's now go ahead and clone this newly created repo using Git and open it up in your editor of choice. For reference, I'll be using VS Code. As the template comes with example code, we'll next remove this from the project as it's not required. We'll start by clearing out any files in the images and sound folders in the root. Then do the same in the entities and scene folders within the game folder. Next, we'll rename the main template example game file to Bomberman-game.js and update the class name within this file to match also. Then, in the index.js file, we'll again replace the template example references with the new Bomberman game one instead. And finally, we'll need a default scene for our game. As we're looking to replicate Bomberman's battle game mode, let's create a new file in the scenes folder and call this battlescene.js. This file will look to create and manage all of our entities and any code related to this section of the game. One thing to note, rather than type the initial class code manually, we'll use the handy VS Code snippets I've supplied with the template instead. If you type SDC, an abbreviation of Shez's Dev Corner, you should see that VS Code gives you 3 snippets to choose from. As we're defining a scene, we'll pick the SDC-SC snippet, SC being an abbreviation of scene class. This will provide us with the scaffolding for the file and allow us to rename the class from the get-go. As per usual, we'll mirror the file name for the class and call it battlescene. Moving over to the index.html file, we'll remove the references to the Google font, as again we won't be needing them for this tutorial. And while we're here, we'll update the title to something more appropriate, like Bomberman. Then at the bottom of this file, we'll update the references to use the correct assets files, although that's something we've yet to obtain. We'll only be using image files in today's video, and if you're familiar with my channel, you'll know I tend to rely on the Sprite's resource website for these, and yes, today's no different. So let's head over to that site and navigate to the Bomberman page in the TurboGrafx-16 section, which is unfortunately hidden in the Other Systems drop-down menu. Anyway, once there, we'll need to download and save a copy of the Bomberman, the battle stage, the HUD elements, and the font files. Simply click on the icon for each of these from this page, and then save the image that's presented on the following pages to your project's images folder. You'll notice some of these were ripped and supplied by me personally, as the site never had the necessary files I needed for this tutorial, but hey ho, it does now. We should now have all 4 images in our images folder. You'll notice I've renamed them accordingly. One thing to note however, is that these graphic files tend to not include the correct alpha or transparency channel, and therefore won't display correctly in our game if we use them as is. In particular for us today, this affects the Bomberman sprite image we've just downloaded, so we'll need to correct this using the graphics tool. I usually perform this task using Graphicscale, as it makes it very easy, but unfortunately this tool is Windows only. So to make this step platform agnostic, I'll show you how to go about doing this in GIMP, a Photoshop-esque graphics tool available free for all platforms from the following link. Okay, open up this image within GIMP, and you'll notice that each of the sprites has been placed inside of a magenta coloured box. It's this colour we need to convert to the alpha channel, so that it's transparent when drawn to the canvas. The easiest way to do this is to use the Colour to Alpha option from the Layer and Transparency menu. Selecting this will open a dialog. Notice the selected colour has defaulted to white, and the white Bomberman sprites now have a checkerboard effect applied to them. This checkerboard effect presents the alpha channel GIMP has applied to the image. Now click the eyedropper button on the right, and move your cursor anywhere on the image that has this magenta colour that we prefer to use instead. This will do most of the work for us, but sadly you'll notice this also affects a number of the other colours too. To fix this, ensure the opacity threshold slider is set all the way to the right, and has a value of 0. This should resolve the colour bleeding into any of the others. Go ahead and click the OK button now as we're done. You should be able to export the image and overwrite the previously downloaded file. Note to self, make this a companion video in the future, so that I don't have to keep repeating myself in each tutorial. Back in VS Code, let's now add an image tag for each of the files, so that the browser will load them into memory as it passes the HTML. We're doing this here to remove needing to mess around managing this with JavaScript. We'll also give them a corresponding ID, so that we can reference the loaded image in our code. And with that, the project should finally be ready for us to jump into coding the actual game. So let's take a look at the battle mode in the original game again, and break down some of the things we'll need to create in our version. From top to bottom, the screen is broken down into 3 fundamental parts. The HUD display that sits at the top of the screen, where it shows the scores of the main battle timer, the movable entities that move around the main game area, some of which are controllable by the players, and the main game area itself, which restricts the movements of these movable entities. All of these actors, or rather entities, perform the same 2 fundamental actions on each frame of the gameplay loop. They update their own state, and then draw their visuals to the screen, or for us as web developers, the canvas context. If we take a look at the battle scene we created earlier, it also has these actions already defined, with their own update and draw functions. In fact, you'll notice we're applying the same pattern across all of our entities too. More on this in a little while, but for now, let's start by recreating one of the 3 entities we've identified, the main area and the background for the game, which we'll call the level map. As this is where the main game takes place, and what all the other game entities will interact with, it makes sense to start there. So in the entities folder, we'll create a new code file and call it level map. Just as before, we'll use the included template snippet to create the file structure for us, rather than typing it out manually. Type SDCEC and press enter to produce the entity code, and then rename the class to level map too. As the entity's main purpose is to handle the drawing of the main playing area of the game, we'll need a way of managing this. Let's bring up the battle stage image we downloaded earlier for a moment. On the left is the full image of what we'd ideally like to draw. So if we really wanted to, we could take this and draw it to the screen in its entirety and be done with it. But honestly, I feel this would be cheating. To explain, if we look how the image is formed, you'll notice that there's a lot of repetition in the way it's laid out. This is because there is. There is actually only 3 small sections of graphics which repeat across the full area of the image. The completely grey outer wall, the main grey wall block, and finally the green walkable section. The common term for these small sections of graphics is tiles. If we were to grab just these 3 tiles and then lay them out in the correct order, repeating the pattern as seen here, we'll eventually get the same image too. The data that forms this combined image is generally known as a tilemap, and is exactly what the original game did, mapping out the tiles in a specific order to produce the stage backgrounds, so that it could efficiently use its limited graphics memory. In fact, drawing tilemaps to the screen or a certain layer was pretty much built into the hardware for most retro consoles, and the practice is still popular today, to the point where we have impressive tools such as Tilehead that has been created to help developers to build such things for their own games. That's out of scope of today's video however, but definitely something to delve into at some point in the future. As the tilemap is quite small for Bomberman, we'll do this manually today, but hopefully this will give you more emphasis on its practice. So in the constants folder, we'll create another file called level data. Inside this file, I'm going to paste a tilemap array, which has a number of rows listing the tile numbers that make up the stage image. You'll notice it only has 3 unique numbers, again mirroring the 3 tiles we mentioned. 29 is the outer grey tile, 30 is the wall tile, and 59 is the green walkable tile. So where do these numbers come from? Well, if we were to cut the stage image evenly into a grid of 16 by 16 pixel tiles, you'd get something like this. If we now count them across the image, from left to right, we have a total of 28 tiles on each row, but as the first tile on the grid is 0, the last tile on the top row would be 27. Knowing this, we can work out which numbers would suffice for the 3 tiles we need. The first usable tile for our game is on the second row and is the grey tile, which is located on the second column, so 27 plus 2 equals 29. The following tile is the wall tile, and this is located on the third column, so we have 30. And lastly, the first green tile is located on the fourth column on the third row, so this becomes 27 plus 28 plus 4 equals 59. With all that said, I'm now itching to write some code. Back in the level map entity class, as we're only dealing with the drawing side at the moment, we'll first make the update function simply return undefined for now. Also, as we know this entity is static, and therefore doesn't move, we can replace the position parameter with a fixed x and y coordinates of 0 instead. Continuing to set up this entity, we'll also create a local version of the tilemap, and spread the level data's version onto it, creating a copy of that data array. We'll come back to why we're doing this later in the tutorial. Next, we'll get the stage image data using the document query selector function, and using the stage ID we specified earlier. Then we'll create a new instance of an off-screen canvas and give it a width and height size of 1024 pixels. This value replicates the size of the original game's tile layer, so we'll use that also. I won't go into too much detail of what an off-screen canvas is in today's video, but for today we just need to understand that this is basically another instance of a canvas element, but outside of the DOM. So this means it comes with its own context that we can use to build a stage tilemap off-screen, and then later draw the results back to the main canvas. Finally, we'll call and add a new function that does exactly this, called buildStage. Inside this function, we'll need to iterate over the tilemap array and draw out each tile in the correct location on the screen in the style of a grid. We'll use two for loops for this, one for iterating over the row, left to right, and one for iterating over the column, top to bottom. Inside of these, we'll then return the tile number associated to the location in the tilemap array, using the current row and column indexes. We now need to draw this tile number to the off-screen canvas, stage image. We'll extract this to its own function called updateStageImageAt, as we'll also be using this elsewhere today. This will obviously take the row, column and tile values as parameters. Although before we can continue, for reusability and readability purposes, we'll create a new constant value in the game constant file called tile size, and give it a value of 16, which we know from the previous example is the exact dimension of the tiles we're looking to use. Back in our new function, we'll first need to get the context for the off-screen canvas, using its getContext function. Those of you who are familiar with doing this on the main canvas will notice the syntax is very much the same. Now that we have this context, we just need to draw the corresponding tile section from the main image. Thankfully, my template project already comes with a useful drawTile function, which does most of the work for us. Let's import it from the engine context module and pass on the required arguments. The destination context, which is the off-screen canvas, the main image data as the source, the tile number from the tile array, which is based on the position from the image, and then the x and y position values, where we'd like the tile to be drawn to. As the column and row values are only indexes, to ensure we apply the correct grid scale, we'll multiply those values by the new constant value, tile size. The last parameter is the grid size we'd like to divide the image into, which again we know is the tile size constant value. And with that, the tilemap is now being completely drawn to the off-screen canvas. However, the player is unable to see the result, as it was all done away from the usual canvas context. We'll need to take a copy of it and draw it back there, and thankfully it's very easy to do so. In the main draw function, we'll use the standard drawImage function for the main context, but use the off-screen canvas as the source, using a value of 0 for the x and y position. The advantage of this method is that the complex tile map routine that we have in the buildStage function only needs to be called once when the class is initialized, instead of on every frame. This means we only have one draw call to the main canvas, rather than 360. So you can see how more efficient this method is, and we gain the advantage that it replicates how the original game did this. Let's now go and create an instance of this class in the battle scene class, so that we can call its draw function. In its constructor, we'll add a stage property and create a new instance of the level map class. Then within the main draw function, we'll call the stage's draw function, passing on the context and camera that we inherit from the base game class. I should probably mention at this point, if you're not familiar with either the draw function or the game class, I highly recommend you check out my Street Fighter tutorial where I go deep into these concepts. Basically though, the base game class included in the template creates the main canvas elements for us and returns its context to the current scene, which for us is the battle scene class. This means we can pass this onto any entities that require it, such as our level map class. Before we can test what we've done so far, we'll need to perform a couple more small amendments. In the Bomberman game class, we'll now correct the reference to the remove test scene class with our battle scene class to ensure it's the default scene. Then finally, in the game constant file, we'll set the correct screen dimensions for the game. For the moment, we'll use 256 for both the width and height values. With that complete, we're in a good place to test the current code. As this will be the first time we're doing this, I'm going to click the Live Server's Go Live button at the bottom of the screen, which will host our code on a local HTTP server. As we're using native ES modules and not a single bundled file, this is required so that the browser can request and pass each module file when the page loads. For full details on this, I recommend viewing the video I've attached here. Either way, we'll now navigate to the URL where the extension has hosted the game code in the browser. As you can see, we now have the game Tilemap fully displayed on the screen. Although, if we were to compare this to the original game, you can see we're slightly off with its positioning, mainly because we're missing the HUD at the top of the screen, but also slightly on the X-axis too. Not to worry, the template comes to the rescue here again. We'll use its camera to offset the tilemap as required. So back in the battle scene class, in the constructor, we'll set the camera's X and Y positions appropriately, remembering first to add it to the constructor's parameters, as it's passed into the scene class from the Bomberman game class. But what values do we need? Well, back in the game constant file, we'll add two more new constant values. One that's half of the tile size value, which we'll use for the X position, and then one called stage offset Y, which will give a value of 24. This is the height of the HUD panel, so that it gives the correct amount of space for when we draw it later. We'll now import these into the battle scene class, and use them for the camera's position. Then in the level map class, we'll change the draw image call to use the camera's position now too, using them as minus values. If we now check the results in the browser, you can see it resembles the original game far more closely, but we're still missing that HUD. Okay, let's add that next then. In the entities folder, we'll add a new entity called Battle HUD, and again use the entity snippet to add the basic structure of the file. We'll also again rename the class to match the file name for consistency. Then in the constructor, we'll get the necessary image data, just like before, using the query selector function, but this time using the ID of HUD, to ensure we're referencing the correct image file. As we're again only interested in the drawing side at the moment, in the class's draw function, we'll use the draw image call using this image file as the source, and passing on the correct dimensions for the section we want to draw. We're using the bottom section from this image, as the top section is for the single player mode of the game. Notice we're also using the screen width and stage offset Y constant values here, to be consistent with the other entity classes. Finally, back in the battle scene class, just like the level map entity, we'll create a new instance of it, called HUD, and add its draw call to the class's draw call. As we only need the context, we'll only pass that on however. And now if we check the browser, we have the HUD filling the missing section at the top of the screen as expected. Great stuff. Okay, the stage map is looking a little empty right now, so let's move on to the final part of today's video, adding a playable Bomberman character to the screen and allowing him to move around it. As we're only tackling player 1 today, we'll focus on the white Bomberman, although each playable Bomberman character tends to follow the same rules. By default, they always face towards the camera, which we'll call the down direction. The reason I say this is due to the fact they only have 4 directions of movement, down being one of them, while the others are naturally up, left and right. Each of these directions have 3 unique graphic frames that make up their 4 frames of animation, the first graphic frame taking up animation frames 2 and 4. When they are stationary, they will also show this frame. While moving however, they will continue to move in each of these directions until they become stationary again, or they are blocked by colliding with a wall. All basic stuff so far, although uniquely for Bomberman, if a wall blocks their movement, but there is a space available next to it, they will automatically walk around it for you. For example, if they are currently moving to the left, but the player decides to hold the down direction on the gamepad, depending on which edge of the wall they are closest to, the Bomberman will continue in that direction, or flip in the opposite direction to the next available space, where they'll then move in the direction requested. This behaviour is the same for all directions. Understanding these mechanics gives us a good list of tasks to complete for our Bomberman character. So with that, let's jump back into the code. We'll add a new entity to the entities folder called Bomberman, oddly enough, again using the code snippet and renaming the class to match the file name. Before setting up the class though, we'll also add another new constant file called Bomberman. This will house any reusable constant values specifically for the Bombermen. In this file I'll be pasting some objects I set up earlier that we'll need to use. First is the states for the Bomberman state machine. Initially these are the idle state for when he's stationary, and moving when he's not. Then we'll add the frames map object, which stores the data for each individual animation frame we'll need to animate our entity. Each frame includes a named key string for identifying purposes, and then an array that contains the dimensions for the section where the frame is defined on the image. And finally its X and Y origin offset. For the next object, we'll create another new constant file called entities to house any constant values that are required across multiple entities. Here we'll add a direction lookup object that contains all of our 4 directions. With this now in place, we can add the animations object back in the Bomberman constant file, which lists each of the animation frame sequences. Notice I put these under a move animations property, as we'll be adding other types of animations here in a later video. Each sequence frame holds the unique animation keystring from the frames object, and the number of frames this animation will be on screen for. We have an animation sequence for each of the 4 movement directions, so we can now import the direction lookup we just created too. Unfortunately, I won't be going into any of these subjects today, as I'll just be repeating myself, but I highly recommend you watch my Street Fighter series which does this. I've attached a link both here and in the description. And just before we move on, we'll add a walk speed constant and set it to a value of 40, which will be used for our base movement speed for the single player mode of the game. Back in the Bomberman class, we can now continue to set up the entity. As per usual, we'll add the image data, again using the query selector function with an ID of Bomberman. We don't need to create any variables for either the position, velocity or animation, as these are already defined in the base entity class that are supplied with the template as you can see here. We will though define a direction variable and set this to the down direction, which we know is the default direction. Next, we'll add a base speed time modifier variable and set this to a value of 1.2, and then a speed multiplier variable with a value of 1. More on these in a second. And then finally, we'll set up the default animation from the move animations object, using the current direction property, which we know is down. The last thing we need to define is the entity state machine. We know this currently has 2 states, idle and moving, but just for the moment, we'll only define the idle state. Each state will have 3 properties: its type, which will just be a repeat of the state for now, and the init and update functions. The init function will be called when the entity changes state to allow us to set up the initial state change, and the update function will be the logic and behaviour tied to this state, and will be called within the main update function, and therefore on each frame of the gameplay loop. We'll give these properties 2 yet to be defined functions, and then call another yet to be defined function called change state, which will eventually be used to transition from one state to the next. As we currently don't have a default state, we'll pass on the idle state, and also the game time object, which we'll also need to pass into the constructor. This object is managed by the base game class, but more on this later. Let's now create these functions we've declared, starting with the idle init and update functions. We'll be using the arrow functions in this project to ensure we keep the scope of these functions local to the class. Inside the handle idle init function, we'll set the velocity to a new object with its x and y properties set to 0, ensuring we reset the current velocity when transitioning to this state. As for the handle idle state function, we'll leave that empty for the moment. Moving on to the change state function, we'll be using this to transition between the states we have set up in the state machine and to ensure we're in a good place when doing so. This function will take 2 parameters, a new state variable for the state we're transitioning to, and the game time object, which will be passed into the state's init function in case we need it for any time-based logic, such as animation. Here we'll first set the current state property, which will always point to one of the states in the state machine, to the new state variable we've passed in, which currently is the idle state. Then we'll reset the animation frame variable to 0 to ensure we're always at the beginning of the animation, and then set up the animation timer, retrieving the frame data from the current animation. Again, more on these soon. And to finish this function off, let's call the current state init function, passing on the time object. Now, in the main update function, let's finally call the current state's update function to ensure it's being called in every frame of the gameplay loop. So the last thing we need to take care of is the draw call, and for that, I'll paste in some code I prepared earlier. But to walk you through it, we're initially pulling out the frame key from the current animation, based on the current animation frame, which we know is currently the down move animation. Once we have this frame key, we can then get the frame's details from the frame's object, which we know to be their dimensions and the origin point. We're then calling the drawFrame origin function included within the template. This takes a number of arguments, so if we press F12, this should bring up the parameter definition from the template. These are the desired destination context we want to draw to, the source image you want to draw from, the frame array which should include its dimensions and offset, and finally the x and y coordinates. Optionally, the function can also take an array to allow us to flip the image either horizontally or vertically. Here we're using the direction property to enable horizontal flipping, if we're facing in the right direction. Okay, with the Bomberman set up, let's create an instance of it in the battle scene class, alongside the other entities. We'll create a local player property and instantiate a new instance of the Bomberman class. As we know this class requires a position and a time object for its constructor, we'll pass in an object that contains the starting row and column position, as well as forwarding on the game time object from the base game class. Comparing our initial numbers to the white Bomberman starter position in the original game, we can confirm the column X and Y row. We can also add this entity's update and draw function calls to the class's versions of these functions too, passing on the necessary dependencies. Before we can test this however, as these X and Y values are tilemap coordinates, we'll need to convert them into actual pixel values first. So in the Bomberman class, we'll replace the position argument in the supercall with the required calculation. Here we're simply multiplying the row and column values with the tile size constant value, and then adding the extra half tile size value to it to recover it for the frame's origin offset values. We'll do this for both the X and Y coordinates. And with that, we're finally in a position to take a look in the browser to see what we've achieved. And on the face of it doesn't look like much, but to be fair, we now have the Bomberman sitting pretty in its starter position at the top left hand corner of the screen. We also have everything set up for the next thing on the agenda, making him move around the screen based on user controls. In the Bomberman class, we'll now add the moving state to the state machine, and as before, give each of the init and update properties new yet to be created functions, handle moving init and handle moving state. So let's go ahead and create them next to the idle state functions. For the handle moving init function, we'll set the animation frame to 1 rather than 0. This is to show the correct walking frame as soon as the transition is made to the move state. As for the handle moving state function, we'll now have to build out this function, as well as the idle state function that we left empty earlier. This is because their logic is somewhat related. For this reason, we'll create another function called handle general state, which both the idle and moving state functions will call. The purpose of this new general state function is to determine if the player is moving or idle based on the current controls pressed at the time. As for the controls, we'll perform these checks specifically in their own function called getMovement, which will return this new direction and velocity back to the general state function. Before we do this, however, we'll import the input functions from the supplied input handler module from the template, and alias this as a control object, making it easier to use. We'll also give this class a new local property called ID, to specify which player and gamepad this Bomberman will use in the game. If you're not familiar with the input handler, I recommend you check out the attached video, where I go into this module in more detail. But generally, this module basically sets up a number of helpful functions for keyboard and gamepad controls. These are all controlled by the game controls config file. We'll look into this a little more in the next video, but for today, we have everything we need set up. The only thing to note is that the ID we've just created will be used to identify the gamepad for the control helper functions as seen here. Okay, back in the getMovement function, we'll check to see which direction on the controls is currently being held down. Each of the 4 directions is mapped to its own helper function that we'll call with the new ID property. We'll call each of these individually, and if none of these controls are being held down, we'll default to returning the current direction and a velocity object with 0 values, as our Bomberman would naturally be stationary and therefore in the idle state. And likewise, for each of the control directions, we'll do the same, but this time add the correct direction constant value that relates to the control being held down, along with the corresponding x and y velocity values using the walk speed constant value. Now that we possibly have a velocity being applied to our Bomberman, let's ensure we apply this to his position to enable him to physically move around the screen. In the update function, I'm going to call a new function called updatePosition, which will do just that, remembering to pass on the time object. Inside this new function, we'll update the x and y properties of our position object based on the current velocity x and y values, but also using the modifiers we have enabled. You can see we're using the base speed time and speed multiplier values here too, which will come into play later in the series. We'll also use the time seconds passed value to ensure we're applying the correct time delta value. Let's finish off the general state function next then. Based on the direction returned back from the getMovement function, we'll use this value to set the correct movement animation, along with setting the current direction to it too. As for the velocity, we'll return that object back to the calling state function, as it will be used slightly differently in each. In both the idle and moving state functions, we'll first call this function and set the return velocity object back to a local variable. But before moving on, we're going to need another personal helper function. So in the game folder, I'm going to create a utilities folder to hold any global utility or helper functions like the one we're about to create. So inside that, we'll add a new file that we'll call utils for now. Inside this file, we'll create a new function called is0, which, as you can expect, will test an object that has both x and y properties and check to see if they are both 0. Then back in the Bomberman class, we'll add a call to this helper function in both of our state functions. First in the idle state function, where we'll check to see if it's true, and if so, return out early because we know no control has been held down, although if it isn't, we know a control is being held down, and so transition to the moving state. We'll also pass on the time object, as this is required for the change state function. In the handle moving state function, we'll naturally do the reverse. We'll make a call to the is0 function, but this time check to see if the values are not 0, and return out early as we want to know when the controls are not being held down so that we can transition back to the idle state, again passing on the time object. The slight difference in this function is that we'll want to set the local velocity value to the value returned by the handle general state function, as we're already in a moving state. So let's swap that over before moving on. The last thing we'll want to do before checking the changes is setting up the animation. So in the main update function, we'll add a call to a new update animation function, which will contain this logic. Let's create this new function now above, and pass on the time object just like any other update based function. Inside this, the first thing we'll want to do is check to see if the current animation timer variable is lower than the current time's previous value. As the gameTime object will always hold the current live value of time in milliseconds, we can always compare this to our own stored snapshots of it. And that's exactly what we'll be doing with the animation timer, as this will hold the current frame time. So if the animation timer is lower than the current time value, we'll move the animation forward by 1 frame. We'll next check to see if the animation frame is out of the animation bounds by using its length property, and if so, we'll reset it back to 0, causing it to loop, which is exactly what we'll want for the walking animations. And lastly, we'll set the animation timer to its new expected time value, in preparation for the next animation frame change. We'll use the current time previous value, but add the new frame delay from the current animation frame, which we know has an index of 1 in the animation frame array. As this value is just a number of frames, we'll have to multiply it by its frame time value, giving us the actual time value we'll want to wait. I appreciate this was somewhat of a whirlwind explanation for what this function does, so if you'd like to understand animation and the time object a little further, I highly recommend watching the attached video as I explain the subject in greater detail. We should now be able to see the result of our labour in the browser, and as you can see, we can now move around the screen using either the keyboard or gamepad. The Bomberman also animates the direction we're moving. Nice! Let's ignore the collision problem for the time being, as we do have another slight issue at the moment. If we were to stop moving, you'll notice the walking animation continues to animate. Ideally, we only want it to animate when it's in the moving state. Let's quickly fix this before moving on. You can actually approach this in 2 ways, but we'll go with the obvious one first, and later in the video we'll explain the cleaner version. In the update animation function on the first line, we'll extend the exit out condition by checking if the velocity is also 0. As we know, we only want the Bomberman to animate when he's moving. Okay, so back in the browser, we're still able to move around the screen and the Bomberman animates as expected, although now if we start moving, he stops animating too. Great stuff. Let's look to resolve the main issue we have at the moment then, and that's the Tilemap or stage collision, to prevent our Bomberman walking through walls. Let's take another look at the getMovement function. At the moment we're just currently blindly accepting that we can walk in any of the directions using the controls. In fact, it's probably wise to ensure we can actually move in that direction before returning back the necessary direction and velocity values. So for each of these, I'm going to return a new function response called performWallCheck, which will check to see if any walls are preventing us from moving in the direction the control is requesting to move. We'll pass in the directions to this function so that we know where to check for the collision. Although at the moment we don't have any collision details for the current tilemap we're using. So in the level data constant file we set up earlier, I'm going to add a new lookup object called collisionTile, which lists each of the collision types. Empty is a walkable tile, meaning there is no collision required. Wall, which is a collision-based tile, but non-destructible. And finally block, which is also a collision-based tile, but is destructible. We'll be looking into block tiles in the next video, so we can ignore this one for the moment. For the collision data, we'll need to mirror the tilemap array, but provide the correct tilemap lookup value for each tile. We'll call this collision map, and I'm going to paste in the array details that I prepared earlier. Wow, there's a lot there, but don't panic. It's simply a one-to-one mapping of the tilemap array above, but using the collision tile object values we've just created. So both tiles 29 and 30 will become the wall value, and therefore 59 becomes the empty value within the collision map array. With this added, back in the Bomberman class, we'll create the performWallCheck function, and at the top of it, we'll create a local copy of the collision map array by spreading the data from the level data constant file. Continuing to flesh out the performWallCheck function, we'll add a further function called getCollisionCoords, where we'll again pass on the direction. Inside this function, I'm going to paste in some code I prepared earlier, yet again. But to explain, we're ultimately taking the direction we're looking to move in and converting the player's X and Y position values into row and column values using the standard tile size constant value. We need to do this so that we can determine where we are on the collision map and understand if a wall is blocking our movement. Walking through the code, we're using a switch statement to return back a unique set of these converted row and column values, based on the direction. The first object is for the closest side of the direction, and the second is for the furthest side of the direction. The reason we're returning a set will become apparent in a moment. We're also offsetting the X and Y values differently on each, to ensure we're checking for the collision correctly, again based on the direction we're looking to move into. Now that we have this array with the tile collision coordinates, we can check to see if we are indeed impeded by a wall. Yes, we'll be creating another function that we'll call shouldBlockMovement, and pass on the collisionCoords array, which as you can expect from the name, will either return true or false if something is blocking our movement. If this is true, we'll therefore return the current direction and a zero valued velocity object back to the getMovement function, similar to the default return in that function. In this new function, we'll first check to see if both items in the collisionCoords array are the same, by comparing each of their row and column values. If you remember, Bomberman has a unique movement behaviour in that it automatically walks around a wall corner for you if it can. This is the main reason we have a set of collision map coordinates, as we're using them to check the collision map so we can perform this behaviour too. So for us to do that, we'll first need to check the collision tiles from the collision coordinates we've collected. We'll add a new local variable called collision tiles. This will be an array that calls, yep, you guessed it, another function called getCollisionTile, passing on each index of the collision coordinates array. This new function is simply a small helper function for the collision map array, which will return the value at the specified row and column position. Although before creating this function, let's continue on. In the first pass, we're going to return true if the collision coordinates are the same, and one of them has a collision tile value of wall, or they both have a collision tile of wall. As a side note, you may notice that we're using a equals or higher comparison here. The reason for this will become more apparent in the next video in the series. Anyway, if neither of these conditions is true, we'll return false. Back in the perform wall check function again, we can continue to complete this function now, as at this point we know nothing is blocking us from moving. But unfortunately we'll need to make one more addition before doing so. Jumping to the entities constant file, we're going to create two more lookup objects, both of which I'll paste in again. First is the movements lookup object, which provides a lookup map for the velocity values based on the direction. And second is the counter direction lookup object, which provides a lookup for the inverted navigation based on the direction. So both the left and right directions are up and down, and vice versa. We'll be using both of these to help with the Bomberman's unique walking behaviour. So back in the perform wall check function, we now have everything we need to finally complete it. We'll start by retrieving the counter direction from the lookup we've just created. Then, we'll perform a check on both the collision coordinates, because we know at least one of them is empty at this point. We'll retrieve the collision tile and check to see which one is a wall. Depending on which one it is, we'll return the corresponding direction and velocity based on the lookup objects we've just created. These two return objects should give us the unique behaviour we've been looking for. Nice! And finally, if neither of them is a wall, then we can just continue to return the direction and the velocity the controls requested all along. One quick thing to note, you'll notice I'm spreading the movements lookup object each time I use it. This is because I want to make a copy of it and not pass on its reference. Otherwise, this could lead to all sorts of unwanted behaviour. Oh, and before I forget, let's go ahead and add the missing getCollisionTile function. We'll add it alongside the other get functions at the top of the class. This will take a tile parameter, which will be an object with both the row and column properties. So we'll use those as index properties on the collision map array, which will return the collision tile value at that position. Finally, at the top of the class, we'll swap around the speed properties. We'll first change the base speed time from the 1.2 value we currently have to the walk speed constant value, as we know this is the default base walk speed time, and then change the speed multiplier value from 1 to the 1.2 value to set the default speed multiplier for the battle game mode. And breathe, because with that, we should be able to see some exciting results in the browser. If we now attempt to walk around the screen, you'll notice we're unable to walk through walls, as the collision map is set up correctly, stopping us from doing so. You should also notice that the unique movement behaviour is in place too, meaning the Bomberman will automatically attempt to walk around wall corners as expected. Excellent work! And just before we finish up with some light refactoring, let's add some debugging functions that I like to add for development purposes. In the game constant file, we'll add a new constant value called debug and set this to true for the time being, but we can toggle this on and off as needed however. Then in the Bomberman class, in the draw function call at the bottom, I'm going to make a check to this boolean. If it's false, we'll simply return early and perform no debugging draw calls, but we know it's currently set to true, so let's add some. In the utils folder, I'm going to add a new file called debug, and inside paste a couple of functions I prepared earlier. These are the draw cross function, which simply draws a cross at the position using the colour you specify. This is useful for displaying where your entity's X and Y position currently is on the screen. And then a drawBox function, which is self-explanatory too. It draws a box to the screen based on the dimensions array and colour you pass into it. This is useful for drawing boxes to the screen, such as collision boxes. Let's now use both of these within the Bomberman class, so that we can physically see the position and the collision boxes. We'll start with the drawBox call and pass on the current context, camera, a dimensions array using the current X and Y position, and the tile size and the half tile size constant values, and finally a colour of yellow. This will be useful showing us the collision area with both the collision and tile maps. Then we have the draw cross call, which follows the same pattern, passing on the current context and camera, but we now pass on the X and Y object with the current position values, along with the colour of white. As mentioned, this is useful for showing the current Bomberman's position. Taking another look in the browser, we can see both the box and the cross displaying over the Bomberman's entity, providing us some possible useful information for development and debugging purposes. Those of you who are familiar with my other videos will know that I like to finish my tutorial videos with some refactoring. We collect a better understanding of the overall code as it develops, so taking a small break every now and then to refactor is a healthy habit to get into. The first refactor is actually going to be a bug fix in the Bomberman class. In the change state function, we actually forgot to use the frame delay index for the animation timer, so let's quickly add this to the animation variable. We'll also move this line down under the current state init call, so that it correctly uses the animation frame set in the init call, as we know we set this to 1 when transitioning to the moving state. For the next refactor, we'll move the hard-coding value of 1024 over to the level data constant file, so that it's configurable, and also so that it's clearer on what the value actually is. In that file, we'll create a new constant value called StageMap max size, and give this a value of 64, and multiply this by the tile size constant value, giving us the 1024 value we want. We're doing it this way to again make it clearer that the max size is actually a multiple of the tile size. Then in the level map file, we'll just import this constant and replace the current 1024 value with it. While in this file, let's also look to optimize our update stage image at call by moving the stage image context variable out of this function and into the constructor instead. We're doing this as it's a little wasteful to keep getting the same context every time we make the draw tile call, as the context variable never changes. So it makes more sense to get the context once the class instantiates, and then store its reference for later use, removing the need to do it on each update stage image at call. Once we've moved it and given it a local property, we'll use that back in the function for its context argument. Another small change I like to make is to the screen height value we have in the game constant file, which currently has a value of 256. We'll change this to 224 to more resemble the original game. Short and sweet, that one. And finally, for the last refactor, we'll come back to the update animation function and take another look at the isZero function we're currently using. I'm going to replace this by using the current state's type property instead, comparing it to the idle state. This gives us the exact same use case but limits the condition boundaries to just the idle state. This makes more sense, as we would never want to animate while in this state, whereas if the velocity is 0, we could potentially still want to animate, for example when we die. And with that last change, let's jump back into the browser for the last time today, so that we can ensure we've not broken anything with those refactors. Phew, it seems everything is still looking okay so far. The Bomberman still walks around the map as expected, with the collision still intact also, but we now have the animation's initial walking frame working better. The screen height has also been shortened somewhat, to help remove the excess tilemap, and the idle state still works as we don't animate unexpectedly either. Good stuff. So that's where we'll leave it today. As you can see, we've made quite a dent into this project already. But what's a Bomberman game without bombs, am I right? Well, that's an excellent question, and something we'll look to resolve in the following video, where we'll look to add destroyable blocks too, along with power-ups to help with the gameplay. We'll also unfortunately allow our Bomberman to die, if he touches the bomb's flames. So yeah, there's still plenty to get on with, but that's where I'll sign off for now. Thanks for watching, and I'll hopefully see you in the next one. And out.